Hello. The most important discovery of astronomy was how far away things were, how far away the stars are, how far away the other galaxies. This discovery, more than any other, has defined the modern thinking about the universe and our place in it. It's no wonder that people want a small, finite universe. It's easier to understand, it's easier to deal with, it feels more comforting. But it's just not the case. So how do we know how far stars are? Well, billions of dollars have been spent on equipment to find those distances, and we now have very accurate distances for tens of thousands of stars. But I wanted to see what I could do with the simplest possible equipment. Well, here it is. A tripod, a camera, a 50mm prime lens. Could use any kind of lens, but I like the prime lens. Now set on f/16. And this. A 100,000 neutral density filter. Just line it up. f/16, 1/4000th of a second, and we take a picture. Now we have all of the sun data. We have to wait for dark to get the star data. I picked Sirius as my first star to get distances, and of course used the absolute value, absolute magnitude of Sirius and the Sun to allow me to compare my result with everyone else's result. Had I not done this, Sirius would have been somewhat closer, though still very far away, 1.8 light years instead of 8.6. So I took a picture of the Sun with an eclipse filter, and then that night I took a picture of Sirius. I then used the color picker in GIMP to find the colors and average the colors to get an average brightness. I then worked out the areas. If you multiply the brightness by the area, you get the brightness concentrated in one pixel. The area of the star was a little tricky. Here's a picture of the star. The star is actually a point. It's a point of light. It's smaller than 1 pixel, but the lens smears it. But I wanted to do something very simple, so I divided the area of the image of the star into 3, a circle and 2 rectangles. Measuring the intensity of each of the areas, I got this. Of course, I had to subtract the small circle from the large rectangle, but that was pretty easy. When I worked this through and fed it into the inverse square law with the distance to the Sun, 1 astronomical unit, 8.3 light minutes, which I converted to light years, of course, I obtained an astounding result. Everyone says Sirius is 8.6 light years away. That was measured in the 19th century, and again many times in the 20th, and again with the unbelievable accuracy of the new satellites. And my value was 8.6 light years. I'm sure I must have done something wrong. Since I was with Sirius, I felt I would go on to Orion, at least get the 4 outer stars, Betelgeuse, Bellatrix, Rigel, and Saif. Here's the table of my results there, compared to the accepted results. You can see my error was less than 20%. I would have accepted anything in the same order of magnitude, not just a mere 20%. So I'm quite pleased with these results. Now, some people might wonder about the absolute magnitude, whether we could do something about that. So to approach that, I used M4, globular cluster, in Scorpio. Here's a photograph with a 135mm lens. That little smudge over by Antares is M4. It contains thousands of stars. Here is a photo from the Hubble telescope. The stars are different colors, you notice. The color classification, or the spectroscopic classification, can be remembered as O be a fine girl, kiss me. O's are blue, rare, and very hot. M's are dim, red, and fairly plentiful. Most of the stars are in the A's through G's. The Sun is a G. I just picked a few that looked right for what I thought were the different spectral classes. You can see those stars I picked here, and worked out their area and their brightness and their blue-red color index. I just took red value and divided by the blue value. And I got this result. If I'd spent a month or two working on this photo, I would have come up with what I've sketched here, the Hertzsprung-Russell diagram. The Sun, by the way, is 1 on this diagram, right in the middle. But I just took the results for the different spectral classes from the Hertzsprung-Russell diagram, the official one, roughly, and here's what I got when I scaled the two. Pretty good agreement for somebody who spent probably not more than 15 minutes with GIMP getting the areas and the colors. So that's it. That's how we can do it. Find a globular cluster that's very far away, so far away that the stars are essentially all at the same distance. Find their brightness then, and we can get the absolute magnitudes. I'm very pleased and excited by this, and I can say to any conspiracy theorist or flat earther that I've done my own research. Thank you.